Okay, so we may start our lecture 3. Thank you for coming to this lecture 3. So we will continue to continuous time filters for today's lecture. So for lecture 2 is also recorded last time and video slides are available. You can check out my courses. And please note that your learning is most effective when you actually attend the lecture. So you are highly encouraged to attend the lecture. And I'd like to make an acknowledgement for technical discussion and inspiration for lecture 1 and lecture 2, 3. So Dr. Kunmo Kim and Dr. Myung-Jun Kim, both of them are quite excellent engineers. All of them are my friends. So senior engineer at Qualcomm and analog I/O designer at Samsung. So you are welcome to ask questions at any time during the lecture. So you can also post questions. It's all the same, right? For the Presimo platform. So scan the QR code, access code is here. Right, and then CH exercise 2 reminder. Please submit a report answering the questions specified in the CH exercise 2 instructions. And deadline is next Tuesday, January 2026. And late submissions will be graded with 0.5x score multiplier. And for quiz, so we evaluate the quiz and we will share the quiz outcome by the end of this lecture. Please help us to recognize your quiz set with a clear handwriting. And what are we going to run in lecture 3 today? So intended learning outcomes. So we will have feedback to understand what is a two-integrator loop representation of second-order systems. And we will check a Laplace transform again, Laplace domain, characterization of pose and Q factor, and time domain responses. So we will be a bit more complicated for today. And we will check stability relationship between damping factor or Q factor. This is related to both sides and phase margins that we discussed at the last lecture, last slide of our previous lecture, lecture 2. Okay, so this is online. We will go on second order low pass filter, feedback theory, Laplace transform, stability analysis, and we will discuss about quiz 1 at the end of this lecture. So for the feedback theory, so we discussed last time second order, very simple, RC low pass filter here, and RC, and we derived the transfer function like this. And it is quite in a format of second order system, right? And the system parameters are given here. Omega 0 is 1 over R1C1, R2C2. And Q factor is square root R1C1, R2C2, here, omega 0. Inverse version of omega 0 over R1C1 plus R1C2, R2C2. So there was a typo actually in lecture 2, was written as a 1. So please check. This was a typo, and actually this format is the more correct one. So we will have a look on actually intuitive analysis. Indeed, it will be skipped because this is quite simple and there is no big difference that we did in the previous lecture. We can also take S equal to 0. And magnitude of S going to infinity, then we can take, okay, C1 is open circuit or short circuit. According to that, we can think about it, then V out is approximated as a V in. And if C1, C2 are short circuit, then V out is always ground, right? 0. So, we will check the feedback theory as the first step of analyzing this second order system more further. And Laplace transform and stability analysis. Okay, let's check the feedback theory. We checked our RC circuit in terms of feedback theory, right? That we used this formula, closed loop gain. Closed loop gain is open loop gain over 1 plus beta open loop gain. So beta is feedback factor here, right? And input and output are there. And we call, again, loop gain. T is equal to beta times A open loop gain. So by this moment, maybe we may think about, we may not think about the transfer function of RC circuit itself. So this is a more simplified circuit, the equation, right? Rather than this, it will be much more helpful to analyze these kind of equations better rather than using R1C1, R1C2, blah, 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 and so on and so on. Okay, so in lecture 2, we analyzed that we derived from RC circuit to this feedback diagram, right? And we concluded that in this kind of low-pass filter, to build a low-pass filter, we need to have one integrator, omega p over s, and one feedback loop. Those are essential building blocks of a low-pass filter. Then we will focus on integrator when we rearrange this equation to derive this kind of feedback theory and the feedback diagram formula. Then maybe we can arrange this equation more difficult formation by focusing on integrator. So because this integrator has an omega 0 over s form, and then our numerator, for example, here, right, open loop gain should be corresponding to numerator part. It doesn't look like an omega 0 over s formula, so we can divide both of denominator and numerator by, okay, so in this case, we can divide by this part, right? Omega 0 over q times s plus s squared. Now it looks like numerator looks like more similar to something over s formula. Then we can further reorganize this equation more simpler format rather than this to make sure, okay, now it looks like more kind of one over something, and the something corresponding to s part, s term. Then plug in this equation into closed loop gain formula here, right? So for this, open loop gain corresponding to 1 over s over q omega 0 plus s squared over omega 0 squared. And the feedback factor is beta is equal to 1 because here now we have a loop gain. It's exactly same as the open loop gain formula. T is equal to open loop gain. So here we can take beta is equal to 1. Then we can build this kind of building diagram. So now we have beta is equal to 1, so we can just simply connect like this, unity gain feedback formula. And the open loop gain is now corresponding to here, 1 over s over q omega 0 plus s squared over omega 0 squared. And we know actually in this kind of second order low pass filter, we know there are two poles. So we can maybe go even further because now we have right s squared or something in this formation, right? That means we can further have a look on this equation, right? Here, 1 over s something something plus s squared is equal to 1 over s over omega 0 formula. So here, s over omega 0 is actually indeed the inverse of integrator formula that we have discussed, and 1 over q plus s over omega 0. This is also the same. Right, the focus is still integrator, and there are two integrators. We can find it. Then we can more like divide our building diagram here. I just separated 1 over s part. That's it. Nothing special. It's just mathematically easy, right? Then 1 over s over omega 0 plus 1 over q here, and omega 0 over s. I just simply rearranged the equation. Then we call, as we discussed in last lecture, we call the first part as a lossy integrator, and the second part is a lossless integrator. For the lossless integrator, is as I discussed, this is this is the form of the ideal integrator. As we take s equal to 0, then its transfer function goes to infinity. That's the ideal integrator, and we call it a lossless integrator. And for the other part, we call this one as a lossy integrator, because even if we take s equal to 0 here, right? Even though we take it, then the magnitude part is just equal to q. It doesn't go to like infinity for the transfer function magnitude. So it's kind of we are losing something. It looks like, so we call it a lossy integrator. It's exactly same as first order low pass filter equation, and then we call this kind of architecture as two integrator loop topology. So it was published back in 1988 by Professor Sanchez Silencio from, I think it was Texas A&M University. So this is quite has been very popular and affecting many areas of our field of low pass filter. And indeed, we can actually switch the order because there's nothing difference. Just mathematically is equivalent, right? If we just put this S over omega 0, the latter or former, it doesn't matter. So this goes to lossless and lossy. It's also same as lossy and lossless. Same. And then, then we can maybe go even further within this formula, right? Lossy integrator, right? So it has a first order low pass filter formula. Then we can go even further as we discussed last time. Then we have, okay, maybe we can rearrange this equation to this, to have like something over S formula. Then open loop gain, now we have, it's more simpler than previous equation. Then we can have open loop gain is equal to omega 0 over S. And the loop gain part, now we have, it's not equal to open loop gain. T equal 1 over Q times omega 0 over S. In this case, the feedback factor, beta, is equal to 1 over Q. Then our final building block looks like this. It has two feedback loops, and two integrators. And this kind of overall building block diagram can be expressed with this kind of system parameters as we derived last time, omega 0 and Q. And we can also switch the order, right? Then if we put lossless integrator first and lossy integrator second, then the ending up with this kind of building diagram is a lossless integrator and lossless integrator inside of lossy integrator. So in the end, two integrators and two feedback loops that implement the second order low pass filter. So key idea is that in general, a second order system can be analyzed using two integrators plus two feedback loops using one of these two architectures. One of lossless first, lossless last. We analyzed our second order low pass filter using omega 0, but we know that there are two poles, right? So it cannot be described with only one omega 0 something. Of course, we have Q factor, but it'll be more interesting to analyze the exact pole locations because those two poles are different. Consider, for example, if we take C1, it's not equal to C2. We have a C1 and C2, each of them are serving as integrators, right? Then if C1 is like 100 times smaller or 100 times bigger, then definitely the two pole locations will not be the same. So we will need to go toward analyzing the exact pole locations to better understand what is happening here. So now, from now on, we may not think about just RC low pass filter. Now it becomes general second order system. So we are not constraining ourselves to RC low pass filter. We will generalize this transfer function. And then as high school graduate, you all know this quadratic formula, right? So we can just apply this quadratic formula to denominator. Then we can get pole locations as this. As 1 equal to, you can do the math calculations. And it's described with minus omega 0 times 1 over 2q plus minus something. And as a reminder, this minus term doesn't mean that we are considering physically a negative frequency. We are just describing what response is required to make this system unstable. That means the pole locations. And for there are some conditions because we have square root term here, right? If this 1 over 4q squared minus 1 becomes negative. Oh, you have a question?
Just clarification. Unstable or stable?
If we apply these pole locations with e to the power of st, then it becomes the system is unstable. So you can have a check again in lecture 2 for Laplace. Exponential, yes, exactly. Growing exponential. Thank you. I brought cookie, not chocolate from London. So we have this kind of specialty when we think about our pole locations. This is a result of quadratic formula, right? If we take this inner term as a negative one, then it becomes imaginary pole locations, right? So we may need to think about it. First of all, if we take a q factor equal to 0.5, then the inner term of the square root becomes 0, right? And the 2q becomes to 1. That means, okay, now we have pole locations. 1 and 2 are exactly same at equal to minus omega 0. So we call 2 equal real poles are there, and this is a condition of critically damped. We will talk about it later more. And first pole and second pole are defined as omega 0, exactly same as this one. If we take q factor less than 0.5, that means 1 over 4q squared is larger than 1. Then there is no mean to make this inner term as negative. There is no way to make this square root becomes imaginary. Then we call it, okay, 2 distinct real poles. There's no imaginary pole terms. So we call it as overdamped. And now we are facing special case. If we take q factor larger than 0.5, then this term within a square root becomes negative. That goes to imaginary. So in this case, we can take imaginary part, j part out, and we can take minus 1 for the inner term of square root. So in this case, we have 2 complex conjugate poles, and that goes to underdamped condition. And I mean, those are kind of looking a bit complicated. So maybe we can take this, take a closer look of this one, 1 over 4q squared. This is actually 1 over 2q squared, and 1 over 2q squared, and 1 over 2q we have here, right? So we can maybe simplify even further by defining this one as a damping factor. Sorry, there is a mistake. So if we define like this, then this is correct. So we can define a damping factor as a 1 over 2q, right? And we can substitute this term as so we can define we can redefine the other conditions like this. For q factor equal to 0.5, now we have defined damping factor zeta as 1 over 2q. Then this condition becomes zeta is equal to 1. And so the second condition becomes if zeta is larger than 1. And now our equation becomes like this. Zeta plus minus square root zeta squared minus 1. And the third condition becomes if zeta is less than 1. Then we have zeta plus minus j, imaginary, square root 1 over zeta squared. So we can rearrange this formula more simplified version here, right? So we have, again, 2 equal real poles. That means critically damped. Now we have a more simpler form. If zeta is equal to 1, we call it critically damped. If zeta is larger than 1, we call overdamped. So over means something zeta is, something over value, right? And if zeta is less than 1, we call underdamped conditions. And before we jump into the next section, we can think about general second-order system, special case. Not the second-order system with 2 two integrator in a single loop formula, there is another way to build second order low pass filter by just cascading the first order low pass filter too, right? In this case, what will happen? So we can think about, okay, maybe we have omega 1 over S, omega 2 over S. It's just simply this derived as a low pass filter like this, right? As we did for first order low pass filter, RC low pass filter, very simple one. Then our transfer function becomes omega 1, omega 2 over something omega 1, omega 2, omega 1 plus omega 2 S plus S squared. So this is also the same condition, right? For the second order system, we have S squared something term in denominator, and the numerator we don't have any S term. The system parameters omega 0 is equal to square root omega 1, omega 2. And what will be the Q factor's maximum value? 0.5, right? Why? Do you remember?
A plus B is 2 squared of AB.
Yes, thank you. So if you're not sure why this becomes 0.5, please have a check. Thank you. Please have a check on lecture 2. We have discussed. So in this condition, zeta is actually larger than 1 or equal to 1. This is the condition for cascading the two first order low pass filter, right? That we have, polar locations of generalized transfer function of our second order system has this kind of conditions, right? For zeta is equal to 1, zeta larger than 1, zeta less than 1, we have different pole locations, different pole equations like this. And in our case, for cascading the two second order low pass filter, it's not possible to build this imaginary term, right? Because our zeta is always larger than or equal to 1. So not possible with a cascaded first order low pass filter. Okay, so we can make maybe have a break for 10 minutes. So please have an attendance check-in by scanning this QR code. This is there's no impact of any grades, but this is for our course analysis. We will be very much appreciated if you can do this. And you can also post questions to the Pressable platform, so we can have a break until, let's say, 48.
One question regarding what I asked before also. So independent of the degree of the filter, when we try to find the range of convergence, we always require that the real part of all the poles are negative.
To make sure your system is stable.
Yeah.
Yes, for the causal system.
For all kind of degrees. I mean, it's not only for second degree, it's also
all kind of filters,
okay.
As you understood. Otherwise, for our causal system, the t is a positive, right? Then if we multiply with the exponential e to the power st.
Yeah.
So only way to make sure our system is alive, then we have to decay exponential.
Yeah. So okay. Just clarification that I understood it.
Yeah, thank you. Yeah. Okay, so let's continue our lecture. So we will go to Laplace transform part as the second topic. So we're not considering RC filter not anymore. So we are moving on to general second order system. So we have transfer function like this. And indeed, when we analyze our pole locations with exact pole locations like this, two different poles, then maybe we can factorize our equation further by having this kind of formula, right? For second order just equation, quadratic equation, then we can factorize our equation by s minus s1 times s minus s2. So this is a definition of how we find the poles, but we are more familiar with the format of omega p1, omega p2. Then in that case, we can think about taking minus sign here, and then we can have omega p1, omega p2 as a plus terms. But for the sake of simplification, we will just use S12. It will be clarified later. Anyway, so for thinking of the exact power locations in terms of S domain, then we will use S1, S2. For simplified version of how we analyze our transfer function in terms of real physical domains like omega, there's no such a thing having an omega is minus frequency in our physical world. So in this case, we can think about omega P1, omega P2. Then in our case, well, we can rearrange our equation by using very simple formula, right? 1 over AB is equal to B minus A, 1 over A minus 1 over B. For the case A is not equal to B, then in this case, we can plug in our formula into this by rearranging this equation. Then we have, okay, this denominator part have S1 minus S2 times 1 over S minus S1 here, and 1 over S minus S2. And reminder of what we studied last lecture. Oh yeah, so before we go into the Laplace transform, yeah, we can further simplify our equation by plugging in power locations that we get. So let's say S1 is omega 0 minus omega 0 times zeta minus term here. We had a plus minus term here, right? So we can take minus term for S1, and we can take plus term for S2. Then we can plug in this S1 and S2 equation here. Then we have, okay, we have a denominator part having something like 2 times square root zeta square minus 1, because we currently have both of the S1 and S2 have the same term, right? Omega 0 times zeta, so we can cancel out those terms. And then as a reminder of what we discussed last time, right, at lecture 2, our unilateral Laplace transform looks like this for the causal LTI system, and ht is equal to 0 for negative t. So we are only thinking about the positive t for the causal LTI system. So we call this kind of Laplace transform as a unilateral Laplace transform. And for the Laplace transform of 1 over alpha plus s, for the inverse Laplace transform, it becomes to e to the power of minus alpha t times ut. Here ut is a step function, and the region of convergence, ROC, is like this. Real part of s is should be larger than real part of alpha when we take a negative sign here. So by just plugging in this Laplace transform or inverse Laplace transform condition, then we can find that, okay, for taking inverse Laplace transform, this part becomes to e to the power of s1t times ut. And then the next part, this one, becomes e to the power of s2t times ut, right? So in the end, what it becomes is omega 0 over 2 times square root zeta square minus 1. And then for the other parts are just what we discussed, exponential terms. That is the result of inverse Laplace transform of this transfer function for the second order system. And there's a very, very important one. We are not considering the condition, the case of S1 is equal to S2. Otherwise, our equation just blows up. So this is a condition when S1 is not equal to S2. What happens when we have S1 is equal to S2? That means our zeta is equal to 1 because we don't want this plus minus term to be alive. Then zeta is equal to 1. Then it goes to, okay, our equation looks like omega 0 square over S minus S0 square for S1 is equal to S2. And here I brought the inverse Laplace transform of the condition 1 over alpha plus s square. Then it goes to t times e to the power of minus alpha t plus minus alpha t times ut. So by plugging in this equation, then we finally got this. Okay, if we have S1 equal to S2, then our inverse Laplace transform looks like omega 0 square times t times e to the power of minus omega 0 t times ut, right? So for the omega 0 term here, for omega 0 here, right, it goes to this side. And then we can further generalize our equations. For the transfer function, when we have S1 is equal to S2, that goes to zeta is equal to 1. If we have S1 is not equal to S2, then we can further divide our zeta value. If zeta is larger than 1, then we know that, okay, we have two distinct real poles. For zeta is less than 1, we have two complex conjugate poles. This is what we discussed. And there is a very interesting part. For the second part here, S1t and S2t, well, maybe we can just plug in our equation S12 equal to minus omega 0 something something, because these are our real poles. However, when we think about imaginary poles here, j term, when we take j something into exponential, then by Euler's formula, it goes to some cosine something and j times sine something. So that is some condition we will need to think about. So yeah, let's just plug in this S12 term into here. Then it goes to e to the power of our equations. Those looks complicated, but we can factor out this minus omega 0 times zeta term here, e to the power of minus omega 0 zeta out. Then we have only imaginary terms here. And then by applying Euler's formula, we have e to the power of j times zeta. That goes to cosine zeta plus j times sine zeta. And when we take this similar formula of e to the power of j zeta minus e to the power of minus j zeta, it goes to 2 times j times sine zeta. So we can apply this Euler's formula, then we end up here, right? So we have omega 0 times e to the power of something as a coefficient. And finally, we have sine term here as an inverse Laplace transform. So when we have underdamped condition, when we take a zeta is less than 1, or when we think about Q factor larger than 0.5, there is sinusoidal term included in the impulse response. So here, when we take inverse Laplace transform, now we are looking at the time domain signals of impulse response. That is the definition of Laplace transform, inverse Laplace transform. So now we can better understand what is happening here. Because we have sinusoidal term in our impulse response, when we take step response here, step response, which is defined by integral of impulse response, then we have, for the Q factor rather than 0.5, we have something leaning condition right here in the transient simulation. For Q factor equal to 2, even more underdamped, then we have more fluctuating things. Those are all because of this term, sine term here. Those are coming from sine term. So when we have Q factor less than 0.5, there is no sine term. So that is the result of what we are looking at as a transient conditions, unit step response. So this is it. So by generalizing these kind of conditions for pole locations, which is drawn in the S domain, the real part or imaginary part, then we have a regional convergence, right? So for the regional convergence, it is defined by the smallest magnitude pole, and the right side of that pole, when we have a negative pole, that is defined by regional of convergence. And for Q factor less than 0.5, which means zeta is larger than 1, then we have two distinct real poles here. there's no imaginary term. Only real values are defined for the low pole locations. Then we have omega p1, omega p2. And when we have increasing Q factor that goes to Q factor equals to 0.5 on the other which can be differently described with data equal to 1, then we have two equal real poles here. It's actually here. That is called as a critically damped. And when we take even larger, Q factor larger than 0.5, then we have ending up two complex conjugate poles, which goes to underdamped condition because our data is less than 1, which is damping factor. Okay, so we can have another break for, I think we don't need like 10 minutes, or maybe we can have 5 minutes. So if you have not completed attendance check-in, so please have attendance. If you have any questions, please, you can ask question. So we can have break until 9:05. All right, so we may continue our lecture. So we will move on to stability analysis. So this is a general stakeholder system. When we plot our transfer function, when we plot our loop gain, which is a stability simulation, that is probably part of CAD exercise 2, then we can get a similar graph, this kind of graph. We have loop gain and loop phase. And loop gain is described with the dB scale. A dB is equal to 20 times log 10 A. This is a dB scale, right? And for the loop phase, we have Euler's formula. By applying this Euler's formula, then we can get the phase response of our loop gain. So we are actually analyzing our circuit when we make feedback like this. Then we have to analyze our stability of circuit to make sure if our stable as it is. And then the system is unstable if closed loop gain goes to infinity. This is the condition of our stability that you probably have run your prerequisite courses. And what it means that our loop gain goes to -1, right here. Denominator goes to 0. That means our system is unstable. Otherwise, when we take t equal to -1, our equation goes to blowing up. To make that happen, so we can think about t equal to -1 that goes to magnitude is equal to 1 here, right? Magnitude is equal to 1. So if magnitude equal to 1, it means that, it is not 1, it goes to 0, right? So 0 dB means 1. You just easily think about when we plug in A equal to 1, then log 10, 1 goes to 0, then our dB scale, it goes to 0 dB. So when we take a look on 0 dB bar, then we can we can analyze, okay, what is the condition of loop gain equal to 1? And at this frequency, if we are thinking about our phase as -180, then it goes to -1, because when we take Euler's formula here, right? Euler's formula. So e to the power of j pi. So 2 pi we have discussed, as we have discussed in our clock playing or playground. Then 2 pi means one rotation, right? 360 degree. And pi means 180. So for pi, then it goes to what is plus 0 and -1. So this describes one of the most beautiful formula in our human history when we search for Google. So anyway, if you cannot recognize what is happening here, what is this guy talking about, then you can have a check of this chapter 10 of this very nice book, Professor Lazabi's textbook, Analog CMOS Integral Circuits. Anyway, this is it for the feedback. And let's assume that dominant pole responses for our feedback system. Then that is very, very typical in analog circuits. When we design amplifier, or if you think about basics of IC design course, you may have designed like two-stage Miller compensated amplifier. Then we can make buffer configuration. Then we are basing this kind of first pole is here, second pole is here. Then we call phase margin, which is defined by the phase response at the frequency of loop gain equal to 1, which is 0 dB. And the difference between 180 and the phase response at that frequency, that is defined as a margin of the phase margin. And then we are discussing actually different poles. So those FP1, FP2 are poles of loop gain here. Only this part. Within denominator, within beta times A open, so open loop gain. That is the loop gain. So there are poles of loop gain. There are poles of entire closed loop gain. So we are talking about now different things. Poles of closed loop gain is let's say S12. So when we open our textbook, then you may find this kind of graphs. For smaller phase margin, you may find that, okay, our magnitude have this kind of gain picking. For larger phase margin, we have very smooth low pass filter response. For the small phase margin, you will find your response, transient response looks like leaning, as we discussed, because of sine term, right? And the fluctuating. For the large phase margin, it is okay, like going to smooth conditions. And then, actually, those phase margins are defined by loop gain response when we think about T equal beta times open loop gain. This is because of loop gain response. I mean, this is discussed within loop gain response for the phase margin. But our stability analysis, I mean, our frequency response of closed loop gain and inverse Laplace transform, unit step response, and so on and so on. Those are closed loop gain response, A closed. They are different, but they are somehow linked up each other. So there must be a quantitative relationship between poles, between phase margin and time domain behavior. Those are our part of goal of our lecture to think about. So let's figure out what is happening here. So for the stability analysis, we will need to go back to our transfer function here, sec of the system, omega 0 square over omega 0 square plus omega 0 over q times s plus s square. Then as the same as we did, open loop gain, feedback factor, and loop gain, we can define like this. And let's have a closer look of this loop gain part, which is the beta times open loop gain. And it goes to, okay, for the loop gain, we can further divide by two factors as we did, right? Omega 0 over s, omega 0 over s plus omega 0 over q. So that means our first part, which is the lossless integrator, it means that it has pole location at s equal to 0. So pole means when we take a denominator as 0, that means the condition how to find the pole, right? So to make sure that happen, we can just simply take s equal to 0. So that means pole is located at s equal to 0. And the second part, the lossy integrator, that we can find that pole is located at s equal to minus omega 0 over q, right here, denominator part. Or in other way around, we can describe pole is located at minus 2 times zeta times omega 0, because we defined zeta equal to 1 over 2 times q. Okay, then let's have a closer look that we have seen in previous slide. Let's assume that we are looking at very, very zoomed up diagram here, graph, loop gain equal around loop gain equal to 0. So to find out something related to our phase margin, we have to analyze what condition goes to loop gain equal to 1, the magnitude condition, right here. So we define loop gain as this. This is coming from the second order system equation here. Then, yeah, let's figure out. When we take the magnitude response of loop gain, then we can further reorganize the equation like this. Omega 0 square over something plus s square. Then when we take the magnitude, then we have omega 0 square over something here, right? This something is defined when we take s equal to j omega. We are applying s equal to j omega because when we analyze our body plot or loop gain or loop response, we are applying the steady state responses. We are applying just a sine wave, single frequency or multiple frequency. We are not applying exponentially decaying or exponentially growing conditions as an input or output. So we take s equal to j omega. Then when we plug in our s equal to j omega, then this s square part becomes minus omega square, right? Because j square becomes minus 1. And for this part, we can just plug in j omega here, right? J times 2 zeta omega 0 times omega. And we take the magnitude, then what it becomes? When we take the magnitude, a plus jb magnitude, it becomes the square root a square plus b square, right? This is what we have learned in previous lectures or previous courses that during the prerequisites. Then we end up at the denominator part, omega to the power of 4 plus 4 zeta square times omega 0 square times omega square. It looks a bit dirty. This is what it is. And when we take the overall magnitude response equal to 1, then we can finally find what is the exact frequency that is meeting loop gain equal to 0 dB. So, yeah, we can rearrange this equation. Then we get omega to the power of 4 plus the other terms here. And then we can take out omega 0 square and minus. Then we have this equation. Again, we can simply apply this high school level quadratic formula. Then we get omega square. So here, omega to the power of 4 is actually some variable of x square. Then we take x square and omega square as x. Then we get the equation of some like quadratic equation. Then we get quadratic formula. We have omega square equal to minus b here, minus b, and 2a. So that means 2 times zeta square, something. The rest of the things are beta square minus 4ac. And we have plus minus sign here. And then, there's a difference, right? And then we can actually take out the inner omega 0 square term here, right? So when we are taking out the equation of x square root and the x square, then we take absolute x. So absolute omega 0 square is just omega 0 square, because it is a physical quantity. And there's a little quiz here. So I am taking square root of omega square here. Then the results will look omega 0 right here, because we have omega 0 square. And I take a square root and minus 2 times zeta square plus for the square root of 4 zeta to the power of 4 plus 1. The question is why I didn't take account of minus term. Can you answer why? Anybody answer? I only think about plus term.
Because we are talking of real frequency.
I'm
Right?
sorry?
Because we are talking of real frequency.
Oh, real frequency.
Yeah.
So,
I mean,
can you add more
I
details?
mean that if you take the minus and we have
Mhm.
minus positive, we go to imaginary.
Imaginary frequency,
Yeah.
right? Yes, thank you. That was simple, right? So we are thinking of physical quantity.
Okay.
We are thinking of physical quantity, so we are not considering omega is negative. So we are taking positive omega here. So we are only considering, we are only considering the real frequencies. So there's no such a physical quantity having the imaginary frequency here, right? Minus term. So when we take a minus within the square root, then it goes to imaginary term, which is not existing in our physical world. So we get unity gain frequency. So unity gain here is here, loop gain. Unity gain frequency of our loop gain is defined as this equation, omega 0 times square root minus 2 times theta square plus other things. And now we can have a look and we can have a consideration of what happens at this frequency of loop phase. That is another key point to figure out to calculate our phase margin here, right? So if we can find out this phase as equation, then we can derive our phase margin by just simply getting the difference between this phase value and minus 180. Then we can get phase margin, right? So again, we can think about pole locations as equal to 0, pole location as equal to minus 2 times theta omega 0. Then by applying Euler's formula, here we have e to the power of j theta equal to cosine theta plus j sine theta. When we take when we take reciprocal 1 over x, then it goes to exponential part right here, e to the power of minus j times theta. That goes to 1 over cosine theta plus j sine theta. Then this is the condition what we are facing, exactly same condition right here. So we are considering the conditions when we have some real part or imaginary part at denominator here. So when we take a pole equal to 0 and when we take s equal to j omega, then the first part, lossless integrator, it becomes omega 0 over j omega, right? For analyzing the phase, then we can simply take, if you remember, for analyzing the phase of a times a plus jb, then the phase of this complex number, it goes to arctangent b over a, right? So we are having only imaginary part here at denominator. Then we can think about our imaginary part as a arctangent omega, right here. Here b is equal to omega and a equal to 0. But this one is located at denominator. Then we can take a minus sign because by this formula, Euler's formula. So here we are we have complex number at denominator. So when we are analyzing base for the complex number which is located in the denominator, then we can simply take minus term. So it ends up minus arctangent omega over 0. That goes to arctangent infinity. So if you have a look on how it looks like arctangent, and it goes like this. And this is pi over 2. It is 90 degree. Because we are applying minus term here, then it goes to minus 90 degree. Oh. Let's remove notation. All right. So what about the other term here? Pole location at minus 2 times theta times omega 0. Then we can apply the same principle here. For the denominator part, we can take base of this denominator complex number. Then we can take j part is omega, and the real part, imaginary part is omega, real part is omega 0 over q, and arctangent and negative. Then it goes to negative arctangent, omega over 2 times theta times omega 0. I just simply plugged in q equal to 1 over 2 theta. That's what I did. So this is our base response. For two cases, when we multiply each other in complex domain, then its base becomes 2 addition, right? Because this is the Euler formula. We are considering the case of exponential function. Then if we multiply, then we get plus addition. So this base response becomes to minus 90 degree and minus arctangent omega over 2 times theta omega 0. And when we think about our phase margin, we can now simply plug in our omega unity gain frequency into this phase response equation. Then we get and then we can have a look on the difference between minus 180 right here. So phase margin value is defined at the phase value here, unity gain frequency, and that is subtracted by minus 180. That is defined as a phase margin. That goes to plus 180. That is plus minus 90 degree. That goes to 90 degree minus arctangent that we derived as before here. Omega over 2 times theta omega 0, and when we take when we plug omega equal omega unity gain frequency, then we get this. And then 90 degree minus arctangent, it goes to arctangent. This is because of this equation. When we take some 90 degree minus arctangent to tangent function, then goes to tangent function is defined by sine over cosine. Then we take 90 degree minus something, then it goes to cosine over sine. That goes to 1 over tangent, arctangent x. That is inverse function of a function that goes to 1 over x. So when we take again arctangent, then we get this equation here. So arctangent of 2 times theta omega 0 over unity gain frequency. That is our condition for the phase margin. So when we plug in our equation, now we get this. Phase margin can be described with damping factor. In other way around, we can describe phase margin using Q factor. So this is what I described, and this is what I introduced in the last lecture, right? I briefly introduced what is happening here, damping factor and phase margin, right? And approximation of phase margin. If phase margin is smaller than 60 degree, then it goes to very closer to what is called as 100 times zeta. So this is it. So when we are thinking of phase margin in terms of zeta, the damping factor, now we can analyze what is happening here. For the zeta is less than 1, then we call under damping condition. Then goes to peaking. Peaking is apparent. And if we have a zeta larger than 1, that goes to over damped condition. Then we don't have any peaking, gain peaking. And in the frequency domain, we have linear condition or sinusoidal response here, response for the small base margin, because we have underdamped condition. For the underdamped condition, we have figured out there is imaginary term within the square root that goes to sine wave equation. So phase margin equal to 65 to 70 degree. Again, that goes to Butterworth response. This is because our Q factor is closer to 0.707. And this is why phase margin larger than 65 degree is commonly chosen as a practical rule of thumb. So if you are not sure how to optimize your system, for example, phase locked loops or amplifier or unity gain buffer, whatever it is, if you're not sure what will be best practice to starting point, then you can simply set, okay, I will set just phase margin as a 65. That's a good starting point to design your system. So this is a unified view. So we have discussed standard second order form from transfer function. We have derived inverse Laplace transform here according to different zeta values. And the pole locations are here, right? Different zeta values. And those are governed by the feedback response. And that feedback is again governed by phase margin, which is important. That is determining your damping conditions. For the critically damped, it is fastest response without overshoot. Overshoot is coming because of our sine term here, sine term. So it means without overshoot. If we are taking over damping condition, zeta larger than 1, it goes to slower. So its settling time becomes slower. And if we take under damped condition, zeta less than 1, and it goes to oscillatory or linear response because of this sine term. And please note that it is important. No need to memorize all of these formulas. Instead, please focus on understanding what the poles and zeta tell you about the system behavior in your analog circuits, analog systems. Okay, then we can, yeah.
So in the basics of IC, when doing the project, it was quite impossible to keep the phase margin over, I don't remember what was it, 75. Actually, in practice, it was over 80, what I had. And get fast SR, slew rate, yeah. Is it related to this?
If you are talking about
to the Miller compensated amplifier, it was too high the phase margin. That's why I couldn't make the speed, the slew rate better.
So slew rate means speed, right? How our amplifier is fast enough. So if you are taking phase margin too good, like 80 degree, 90 degree, then we are losing some speed.
Okay.
So that means overdamped condition. So there is a sweet spot when we analyze our circuit. For the Butterworth response, this is described as a very nice sweet spot considering speed and the bandwidth and the stability.
Yeah. Okay.
Yes. Thank you. So, other questions you have? No? Then we can maybe move on to our quiz result. So, you can check your quiz score in my courses, probably by now, or if not, it will be uploaded very soon by our TAs. So this is the statistics of our quiz 1 score. So we have very nice Gaussian-like distribution of the quiz score. So there was only one person who scored the perfect score, 20. And on average, the mean value is 12.1, and some kind of distribution was there. Scores are. So the question one was the spectral analysis and signal reconstruction. So for the continuous time signal xt equal to 4 times cosine whatever something something is sampled at a frequency of sampling rate at 600 Hz and determine the mathematical expression for the reconstructing signal after it passes through an ideal low-pass filter with cutoff of Nyquist rate, and specify the minimum sampling rate required to avoid aliasing. So what it means is that when we sample this signal, then this is a sampling rate, then this is a Nyquist rate. And after sampling, we take low-pass filter, ideal low-pass filter, right, with cutoff of Nyquist rate. This is the question. When we take the low-pass filter as ideal low-pass filter with a Nyquist rate, then as we discussed, if we have, let's take a different color, let's say here. As we discussed, if we have an input frequency band shaped like this, it will be symmetrical. Then mathematically, it will be copy and paste, right? And so on and so on. So when we take ideal low-pass filter, those are all erased because it will be filtered out. So let me erase here. Here. So this is a condition. So for this question one, frequency extraction, 2 point. So how do we extract the frequency? So any kind of sinusoidal waveform can be described cosine or sine 2 pi ft, right? So for this part, it goes to 150 Hertz. And for this part, 450 Hertz. By applying this 2 pi ft equation. Then goes to 150 and 450. And for the aliasing part, we can derive as a Nyquist rate fs over 2, here, 300 Hertz. And that means our 450 Hertz is actually over our Nyquist rate that will be aliased back to our signal band. So component aliases because 450 is rather than 300. And alias computation is here, calculated like this. This is because we are copy and pasting after sampling. So let's say this is copy and pasted. And let's say, okay. So for example, here we have 300 Hertz. If we have 450 Hertz, then it will be also copy and pasted to the negative part, to the both side. That means it will be, after copy and paste, so let's take a different ink value. So if it is copy and pasted, this much is 300, and this much will be 450. So it will be copy and pasted, and it will be aliased back to our signal band. So how to calculate this one? This is a 600 Hertz, and 600 Hertz minus 450. So this is the aliased frequency component. It is exactly same as 150 Hertz. So for both of both of frequencies are now existing at 150 Hertz. So it becomes to 4 times cosine 2 times cosine. And it goes to 6 times cosine. So Nyquist rate, it is larger than, it should be, the sampling rate should be larger than 2 times, the largest one, 4 times 450 hertz. So it should be larger than 2 times 450. It goes to 900 hertz. That is the condition to make sure there is no aliasing. So rotational speed sampling, that's question 2. A fan rotates at a constant speed of RPS equal to 75 rotations per second. The camera captures this motion as we did for the playground, right? With the clock. Then captures this motion at a frame rate of RPS equal to 60 frames per second. Then we can calculate the number of rotations per frame and calculate the perceived rotation, how it appears to our eyes for the rotation speed that would appear in the recording, and determine the minimum frame rate. The minimum frame rate is very similar to what we have seen in the previous question, required to capture the true speed without aliasing. So this is the result, the answer, the solutions of the question. So to calculate the rotations per frame, so we have RPS is defined as rotations per speed, and FPS is defined by frames per second, right? So if we want to derive our rotations per frame, we can simply divide both of RPS number and 60 FPS number. So we can cancel out per second part. So it goes to rotation per frame domain. So it goes to 1.25 rotations per frame. And the perceived speed. So we are looking at the clock that is sampled at 60 frames per speed second, right? So this is definitely slower than the RPS. So when we take 75, then it goes over 1 clock rotation, 2 pi, which is a 360-degree rotation. Then the remaining part is 1/5, right? So remaining part is 1/5 RPS. This is because our remaining rotations per frame is 0.25 times 60. It goes to 15 RPS. And the minimum frame rate is definitely, it should be rather than 2 times 75. That is Nyquist theorem. And this is it. So we have checked that most of us students scored almost a perfect score for question 2. And there were also some students who retake quiz 1. And the question 1 is very similar condition, right? It is sampled at sampling frequency at 700 hertz, and then filtered by an ideal low-pass filter, which is the same condition that we described, that I described. And to determine the original component frequencies here, it is the same, right? For 2 pi t, we can just simply divide 500 by 2, then it goes to 250 hertz. And this one is 750 hertz, right? 250 and, 650 hertz, 600. So for determine the aliased frequency of any component that falls into the signal band. Right. So when we have a look on the frequency axis diagram, then we can also similarly think about the aliased frequency goes to 50 hertz, because now 650 hertz goes to over the Nyquist frequency. So Nyquist frequency now we have 350 hertz, right? 350 hertz is definitely larger than, smaller than 650 hertz. Then our aliased frequency goes back to our signal band, which results in 50 hertz because it's copy and paste. And the reconstructed signal, it goes to, so here, our first part, 500 pi t, it goes to as it is because there's no aliasing. And for the second part, here, right, 650 hertz. 650 hertz goes back to the 50 hertz here. here, 50 hertz. And it results as a 4 times cosine, 100 pi t plus pi over 4. So the 250 hertz, this one, the first part is in-band. We call it as an in-band. And 650 hertz turns forward back to our signal band and passes to the low pass filter. That is what is happening. So we can go back maybe to complete this one. So the resulting one is 4 times cosine 300 pi t here, and then 2 times cosine, instead of 900, now it becomes 2 times 150 pi t. So the resulting one is 6 times cosine 300 pi t. And the minimum sampling rate, of course, we don't want any aliasing according to Nyquist theorem. Then the highest bandwidth times 2 must define how it is for the Nyquist sampling rate. So Nyquist, the minimum sampling rate must be 2 times 650 hertz. So 2 times the largest frequency. This should be less than the sampling frequency to make sure our Nyquist theorem is satisfied. That goes to 1300 hertz. This is the minimum sampling rate. Yeah, so the second question is very similar. So rotation per frame is also similarly calculated here, and the apparent rotations per frame is also similarly calculated because, so here RPS is faster than the FPS, right? So the remaining part is 0.15 rotations per frame here. And then by multiplying this one with frame per second, because we have frame per frame is described here, then we get 3 RPS. This is the perceived or apparent rotation speed, and minimum frame rate is defined here because our highest frequency is 23 RPS. So this is the Laplace. So today we have finished our lecture 10 minutes earlier. So before TAs arrive, if you have any difficulties of CAD exercise, please ask questions here. So everything is clear. I also am curious if everything is clear on CAD exercise instructions.
Can I try to clarify something before the CAD?
CAD.
Like based on the quiz.
Quiz.
That
yeah.
Probably, and I now got it, but if I draw just there, so because we have
Is it a question 1 or question 2?
Question 1.
Question 1. Okay. This one.
So when you have here, we have the copying here. Here we have if we say that, let's say here we have F sampling. Here we have F sampling, half of F sampling. So any mirroring from here, like if we have here also some frequency.
Sorry? So
if we have here also some frequency of the signal.
Are you asking if we are copying and paste here? So
it's a bit difficult to explain where I'm confused.
So in this condition, can I erase this part?
Yeah.
So after sampling, it will be copy and paste of the original frequency band. So it will be like this. This one is copy and pasted. This.
Yeah.
2 fs. And then this one will be also copy and pasted. Let's say this is a 2 times fs. It will be also copy and pasted, and also the other way. This one. So this one is copy and pasted. This one is also copy and pasted here.
So
we open lecture 1.
After the sample frequency, so this is mirrored to the sample frequency.
For f equal to 0, this one is mirrored to the sample frequency. And this one is actually spaced from DC, right? This.
So this distance,
yeah, distance
to the
that is mirrored to, that is centered around sampling frequency, like this.
Okay.
So let's define the distance as x. Then it is mirrored to fs minus x, mirrored to fs plus x.
Okay, I think I got it.
So
when was the rate exam? What was it going on? This one, that was just for the people who made it.
So what?
Yeah.
So sorry, what was the question?
The retake. Itself, like, this one, what are there still retakes for this? That's which one?
The time.
The time.
Yeah, I mean, because there was a retake. How was this for people who didn't make it to the original one? Or...
Yeah.
Okay.
Yeah. Yeah. Oh, okay. Okay. What is the retake is happening around? Yeah. So the retake is for the people who couldn't make it to the class to take the quiz 1. So let's say you're not happy with quiz 1 result, then you can always retake quiz 1 even now. So please contact 2 TAs if you're not happy with quiz 1 result. So you can take another round of quiz 1 retake. So this is lecture 1, right?
Yeah.
Lecture 1 slide. So we are thinking of the copy and pasting condition here, right? So we are taking repetitive replicas of XF. So this one will be copy and pasted at the FS, or 2F, 2FS, 3FS, and so on and so on. If you have wings, then these wings will be exactly, come together, like this, like this.
Okay. Yeah.
Yeah. Good.
Thanks.
Any other questions on any other things related to quiz? Okay, then let's have a break until 10:05, and at 10:05 we can have quiz 2. Thank you.